Today we're going to be looking at moments. Now, moments are always generated by a force acting on a body. Now, depending on the location of that force, there can either be a turning effect or no turning effect. The body can stay stationary or the body starts to rotate. This is probably easier shown and explained when thinking of a lamina. Now, a lamina is a body whose thickness is negligible compared to its width and its length. So it has a substantial area in comparison to its thickness. So you can think of a sheet of paper or a sheet of metal, or on a larger scale, one of those floating jetties that you might see on a camping or a fishing holiday. So we're going to fix one point on this lamina. So this is you putting your finger down on the sheet of paper, and we're going to apply a constant force in multiple different places and just have a think about what would happen. And we can just apply a force to this lamina, to this sheet of paper, in multiple different positions. To formalize this and to actually get an understanding of the effect that the force is having, the turning effect that the force is having, we need to get some values. So we would like to know the magnitude of the force and its distance to the pivot point specified. Now, when finding this distance, we want it to be the perpendicular distance. And this isn't always going to go to the force, so the force is usually drawn as an arrow, but we're thinking of the whole line of action of the force. So we extend the force through its line of action, and we want the perpendicular distance from the pivot point to that line of action. So here we have a 4 Newton force, and we have 3 meters from its pivot point. Let's bring in the definition. Now, the moment of a force actually measures the turning effect that a force generates on a body on which it is acting. So this force is in contact with this laminar body. What turning effect does it have? We can calculate that by multiplying the force by the perpendicular distance. And to just be more specific, what we're actually finding is the moment about a point, and we calculate that with the magnitude of the force multiplied by the perpendicular distance from the line of action. Okay, so always make sure you're considering that line of action. Let's see what happens in this case. The moment is going to be the 4 newtons multiplied by the 3 meters, and we have 12 Newton meters. That's the moment generated by this force. Now, that's the magnitude of the moment, but we also need to add a direction. Which direction is it going to turn? And the two options are either clockwise or anti-clockwise. And I'm sure you can visualize this movement. This is a clockwise rotation. It started to move clockwise, the same direction as you see the hands on an analog clock moving. So in its entirety, the moment here is 12 Newton meters clockwise. Let's see what happens if we actually move this force. So if we move it closer to the pivot point, instead of being 3 meters away, now it's only 2 meters away. What happens to the moment? Well, the moment is now calculated as 4 times 2, and that's 8 Newton meters clockwise. How about if the line of action goes through the pivot point? Well, then technically, our force is still 4, but the perpendicular distance of the line of action from the pivot point is 0. It's right on top of that pivot point. So 4 times 0 gives us a moment of 0. There is no moment. Whenever the line of action for a force goes through the pivot point, there is no moment generated. There is no turning effect. And as we move that force over to the other side of the pivot point, we can once again find the perpendicular distance. This time it's just going to be 1 meter for the perpendicular distance from the line of action to the pivot point. We need to think about the direction. Now that we're on the other side, it would move the body, it would move the lamina in the other direction. It's now moving in an anti-clockwise direction. The whole body is rotating the other way round, in the opposite direction of the numbers on an analog clock. Okay, so in its entirety, that's 4 Newton meters anti-clockwise. In most instances, you wouldn't actually have a drawn body. Either you would have produced a model yourself, or you would have simplified a real-world situation into a diagram. Really, our modeling diagrams should be very simple. Here I simply have the force and its line of action, and from there I should be able to add on the perpendicular distance. This will be the most familiar situation, but we're also going to look at cases where the distance given to us isn't necessarily perpendicular. We might have an angled approach to the line of action, but from here we should be able to always find that perpendicular distance to the line of action for us to find our moment. Okay, so let's get into a few examples. So here I have a pivot point P. I have a force of 20 newtons. To calculate the moment, I need to know the distance, the perpendicular distance from that pivot point to the force. And I just need to multiply these two values, the force and the distance, and the unit is going to be a combination of newtons and meters. The distance we use must always be the perpendicular distance. So sometimes we might need to extend the line of action of the force to make sure we can have a perpendicular approach to the pivot. So extend, draw your perpendicular distance, and once again, it's going to be the force and the distance multiplied. The notation I'm using here just denotes that the moments are being taken around the pivot point P. Be careful to include the direction, so that's either going to be clockwise or anti-clockwise. We don't want to see right or left. We don't want to see up or down. It is a rotation, it's a turn, so it should be clockwise or anti-clockwise. If the line of action for the force actually goes through the pivot point, there will not be any moment. There is no turning effect if the line of action is going through the pivot point. It's not making any turn happen. So the moment is just zero. Okay, so another consideration when trying to calculate moments is that you may be given a distance that is not the perpendicular distance, and that may be accompanied by an angle. We should be able to get an expression for the perpendicular distance, the one that we want. And we can do that by using basic trigonometry SOHCAHTOA. Here we have the opposite, which lets me be using the sine function. And I can say that the sine of 30 should equal x over 2. I get x equals 2 sine 30. Now that I have an expression for that perpendicular distance, I can add it as usual. So it's the perpendicular distance by the force, so multiplied by 10. It gives 20 sine 30, which cancels down to 10 meters. So the moment here is 10 Newton meters. Okay, so let's look at one more case where the distance that we know is not perpendicular. So this diagonal distance is 3 meters. I'll put the angle over here this time. Let's make the angle 65 degrees. Okay, so how do we find this perpendicular distance x? Well, there is a general result for the perpendicular distance in this case, and it will be the hypotenuse, the trig ratio, and then the angle size. So in this case, 3 cosine 65 will give me that perpendicular distance. In the previous question, it's the hypotenuse, the sine function, 30 degrees, 2 sine 30. So you can actually quickly get an expression for the perpendicular distance when working with moments. So let's go ahead and find the full moment. It's that perpendicular distance multiplied by the force, and that gives us 15 cosine 65, and to a couple of decimal places, 6.539 Newton meters, and direction anti-clockwise. In this question, we're asked to find what each of the forces, or we're asked to find the moment that each of these forces will produce. For the 5 Newton force, quite straightforward, gives us 10 Newton meters. And for the 8 Newton force, once again, using that standard format for the perpendicular distance, it's going to be 2 sine 50 multiplied by our 8 meters. and this one's going to be anti-clockwise. So altogether 12.257 Newton meters anti-clockwise. Okay, looking at this example, we realize that we can't exactly have clockwise and anti-clockwise movement at the same time. One of them has to win out over the other. And in the next video, we'll be looking at resultant moments and how do we calculate which direction wins out over the other. Okay, Halima, and we're just about finished. But before you move on to some practice questions, let's take a look at the specification and exactly what it is that students are expected to be able to show. Exactly what the examiners are anticipating you'll be confident in. While you read through, I want to quickly remind you that it will be sensible for you to come back and watch this video at a later date, maybe come back in 2 or 3 weeks as a refresher or just before an assessment. And as you watch through the second time round, the third time round, because you've done your practice, a lot of what you go through here should resonate with you much more, and you have a chance to really embed your understanding of the difficult topics, anything that's been flagged up as A-star.